Hi, my name is John Paul Raj, and I'm on a mission to make the learning of math fun. So if you're new to this channel, please do consider subscribing. On this particular video, we're going to continue our discussion on the instantaneous rate of change, which is the slope of the tangent line, also known as the derivative. Let's start. In the previous video, we already saw the slope of the secant line, the slope of the tangent line. We gave it a meaning, okay? We said that the slope of the secant line was called the average rate of change, and the slope of the tangent line was called the instantaneous rate of change. And we ended that video saying that this is such an important idea, giving us the instantaneous rate of change, which was called the derivative. There is a problem, however, if you're trying to draw that tangent physically, geometrically. I'll explain what I mean by that, okay? So let's say we have a function, something like this, okay? Just any function, f of x. I'm just going to call that f of x, okay? And let's say we need to draw the tangent at a point, at this point, okay? Now watch my construction. And then I can draw a line touching that point at, touching the graph at that one point, okay? So there we go. That's a tangent, right? You'd all agree that's a tangent, okay? Touching the graph at just that one point. However, if I take another color now, and I can say then, using a tool, line tool, I'll try and draw another line now. Okay, and you know what I'm talking about, okay? So now what's the difference between these two lines? You know, they're touching the graph at just one point, right? So let me call this one T1 for tangent 1. This one we can call it tangent 2. Let's say another one, another color. Let's try it out. Touching more or less it'll be close enough. But for those of you who tried to draw a tangent, okay, let me just zoom in. They are touching the graph at that one point, whatever that point was. Let's just label that point also, okay? So that point is some x is equal to, let's call it a. So at x equals a, I am able to do with this simple illustration, you know, 3 different lines, and that depends on how you've placed the ruler. You know, when you're actually drawing the tangent using geometrical tools, you'll notice that depending upon the angle that that ruler is placed, okay, even though it's touching at one point, you can actually physically draw different lines, you know, varying at different angles. So physical drawing of the tangent using geometrical instruments can give us ambiguous answers for the slope of the tangent. The slope of the tangent was what we call the derivative, can give us different answers depending upon how you've placed the ruler, correct? So this geometrical approach of actually drawing the tangent line may not give us an accurate answer. It will give you an approximate answer, close enough, but not the exact value of the instantaneous rate of change. So we need another approach, we need another style. There is a very interesting video on YouTube by Socratica. I'm going to link this video in the description box below. Please go ahead and take a look at this video. It's very interesting, very informative. And they talk about the ambiguity in the definition of the tangent. Okay, so it's very interesting to know that even, not only it's just the physical drawing of the tangent using the instruments, but even the language used to define a tangent can be ambiguous. So there must be another way to find the slope of the tangent line, which is such an important concept, right? This instantaneous rate of change. I've said that so many times. There must be another way to find the slope of the tangent line without actually drawing the tangent line due to the limitations of geometry. We are going to talk about that today. So I'm going to draw another set of axes here. And here we go. That is my x-axis and y-axis. I'm going to label that as x and y. And my function is, let's just say it's some simple function like that. This is f of x, right? And what we're going to do is that we're just going to go ahead and say we want to consider the tangent at some point here, all right? That point, let me call it A. Can you see this? All right, that's my point A. And let's say there's a point B out here, all right? That's my point B. Their corresponding y values, because this is f of x, this is going to be f of b. And this one out here is going to be f of a. This is really small. Okay, you can see that. Okay, first what we're going to do is that we're going to draw a secant line. Okay, so joining those 2 points, we're going to draw a line. And we've already seen in the last video that if this line cuts this curve in 2 different points, that's a secant line. Now we can find the slope of the secant line, right? That's no problem. We've done that in the earlier video also. So the slope of this secant line, slope of the secant line is, using these notations, we can use the formula for the slope y2 minus y1, okay? So that's f of b minus f of a, the whole thing divided by b minus a. All right, can you see this? Here we go. I'll just adjust this. Okay, the slope of the secant line was also known as the average rate of change. ROC is just short for rate of change. So the slope of the secant line, which gives us the average rate of change, is given by the formula fb minus f of a, the whole thing divided by b minus a. And that b minus a in context is actually the distance between those 2 points, right? It's the difference, that's the distance between the 2 points. So it's like saying that the secant line is joining those 2 points whose x values are a and b. The distance between a and b is b minus a. Now, if there is a way to minimize that distance as b minus a becomes really small, I've said tends to 0. That's the language of limits, tends to 0, all right? Then that line, what do you think is going to happen that line? That line is actually going to go, it's going to, if you can imagine with me, that line is going to be traveling this way, this way, this way, because b minus a is going to become really, really, really small. The distance between a and b, it's actually going to look like a line that is just at that point, right? It's going to look like a tangent, theoretically. Let's find out on the calculator. Okay, so here's my calculator. I've already drawn the graph there so that it'll save up on time. Let's just do the other constructions. Okay, so let's just go and say we want to draw a line first. Okay, so let's draw a line that's going to denote, let's just draw it between 2 points on the graph. Okay, this is slightly different from what I've drawn on the iPad here, and so that will stand out. Let me just change the colors. All right, so this one, I'm going to change the color to, let's say, magenta. Let's change the attributes of this line, make it a little thicker. Okay, that's the line, and let's just calculate the slope of the line. Okay, and because we're using technology to do this exploration, we can just find the slope directly, and that is the slope of that secant line. Okay, it's a secant line. As you can see, it's cutting the curve in 2 points. Well, actually, if you extend the line, it's going to cut in more than 2 points. All right, but that's the secant in that region, in that locality. Okay, so that magenta line, its slope is 0.675. Now, all I'm trying to say is that if that distance, this is like the point A that I denoted here, and this is the point B, if the distance between the two decreases, can you see what's going to happen to the slope? Watch what's going to happen to the slope. You see the slope is changing, and it becomes negative as the line starts tilting this way, all right? So as the distance between the 2 points decreases, you can see the slope is also changing. But now, to try and see, what I said was imagine a tangent at that point. Let's draw a tangent. Let's verify whether it's the same thing. Okay, so if I were to draw another line, and this time, let's just choose a tangent line at that point. Okay, I've chosen that, and when I hit escape, this is the equation of the tangent line, by the way. Its slope is negative 2.9, and you can see this is the slope of the secant line, okay? The tangent line is not clear, so I'm just going to go and extend it. And perhaps I'll have to even change the color so that it'll stand out. And here we go. Let's change the color to maybe something like a Dodge blue. And let's change its attributes also. Maybe make the thickness, increase the thickness. So here we go. This is our secant line. This was the original secant line, wherever you want to position that. Okay, and its slope is 0.517. As the distance between the two lines decreases, okay, that's the idea of the limits. As the limit of the distance between them becomes really small, and when I say really small means it's almost approaching, it's like saying B approaches A, right? So this is coming closer and closer. Can you see that? It almost, as the distance becomes 0, there, you can see the blue line, the Dodger blue line is on that magenta line, and you can see the Dodger blue, that was the equation of the tangent line. You can see that the slope is the same. That is the idea of limits that we are trying to bring out here, that we can use the slope of the secant line to try and approximate the slope of the tangent line. How? By studying the limit, by observing that the limit as B approaches A. The limit as B approaches A of what? Of this expression. And what is this expression? This is the slope of the secant line. So the limit as B approaches A of f of B minus f of A the whole thing divided by b minus a. So the limit as b approaches a, that means what's going to happen? We're looking at the denominator and saying, ooh, that's going to become 0. Well, we already saw in the video on limits that it's not about the value. Limit is not what the value is. The limit is the behavior. So the behavior of the secant line is going to be the same as the behavior of the tangent line as b approaches a. In other words, the slope of the secant line will be the slope of the tangent line when b approaches a. The denominator becoming really small. Sometimes some textbooks use the word infinitesimally small, and that is actually like saying it's becoming 0. So that means we're using this expression. This is actually what's inside the bracket is the average rate of change, right? Average rate of change, which was the slope of the secant line. But when you're looking at the limit, use this color here, this limit is going to give me the instantaneous rate of change, which is our slope of the tangent line. Now, using limit, we can get a definite answer as we have already shown here. Like, as the limit becomes 0, that secant line, which was my, what color was it? I don't know. I'll have to just move this point and see what's going to happen. Yeah, can you see that? That magenta line was the secant line. That line, as the distance approaches, becomes small, that b minus a becoming small, you can actually see that the slope of the secant line is equivalent to the slope of the tangent line, and that is precisely what we're seeing analytically. This is the heart of calculus, okay? The idea of limits is the heart of calculus, and what we've seen that the slope of the secant line can be used to approximate the slope of the tangent line, which gives us the instantaneous rate of change. If we were to generalize this idea, this was just for any point A and B, right? If we were to generalize this idea, let me draw another set of axes for that. If we were to generalize this idea, and I'll say a function f of x again, this is f of x, okay? So let's say for any x, here it was a particular value of x called a, here's any x, and suppose we have another value which is x plus h. That means the distance between them is h, right? Between x and x plus h. Let's consider it as a very small value. H is a small value. You can even say very small if you want to. Infinitely small. So whatever the distance between x and x plus h. If there is such a case and we are looking at its y values, all right? So that means you're talking about the y value at this point of f of x, and the y value at this point is going to be f of x plus h. And we consider the secant joining these 2 points, x and x plus h. And then using the idea of limits and the slope of the secant line, we can approximate the slope of the tangent line at any x. Let's do that. So first, let's write down the slope of the secant line, all right? Now, our 2 points are what? X plus h and x, right? So the values are f of x plus h and f of x. So the slope would be f of x plus h minus f of x, the whole thing divided by x plus h minus x. Now, this is nothing but the formula for the slope, okay? y2 minus y1, okay? That's the difference in y coordinates on the numerator. On the denominator, you have the difference in the x coordinates. It's just the formula for the slope. This becomes f of x plus h minus f of x, the whole thing divided by h, because x plus h minus x just simplifies to h. This is the slope of the secant line. And now when we examine the behavior of this slope, the slope of the secant line, as h becomes small, h is the distance between x and x plus h. As h becomes really small, this slope of the secant line will become the slope of the tangent line at that point x. All right, so what we are saying is as limit h approaches 0 of the same expression, f of x plus h minus f of x over h. Inside the bracket is the slope of the secant line. Using the limit as h approaches 0, we get what is called the instantaneous rate of change, which is what? Which is the slope of the tangent line. And we have already seen in the earlier video that this is what we have called the derivative. The notation for the derivative is f prime of x. If fx is the function, then f prime of x is going to be the notation for the derivative of that function. This term inside the bracket, which is the slope of the secant line, is sometimes referred to as the difference quotient. This formula to find the slope of the tangent line using the limit as h approaches 0 of the slope of the secant line, sometimes it's also referred to as the limit of the difference quotient. This formula is called the derivative by first principles. So sometimes you'll be asked questions where it says find the derivative by first principles, and basically they're asking use this formula. So what did we do today? We just saw the same idea of the secant line and the tangent line as we saw in the earlier video, okay? But what did we do? We used the slope of the secant line, the average rate of change, to approximate the slope of the tangent line, the instantaneous rate of change, using the idea of limits, and the limit of what? The limit of the denominator, the distance between the 2 points becoming 0. And that limit is the limit of the difference quotient. And this method to find the derivative of a function using the limit of the difference quotient is what is called the derivative by first principles. In the next video, we're going to use this method to find the derivative of some simple functions. I'm going to see you in that video.